All right, let's jump into 9.2 because math doesn't teach itself, unfortunately. So when those teachers up north, when they walk out with the unions to try and advocate for higher pay for months at a time, the kids don't learn, unfortunately. All right, 9.2, starting a new section today. You'll need a calculator, by the way. So if you want to come up and grab one. I'll go ahead and load my calculator here. Taylor polynomials. Taylor polynomials. This is going to be an intro to Taylor series. What is that, Hampton? A fennel fox. Okay, I've heard of them. All right, so where this year have we already heard the term Taylor form of what? When do we write, okay, pay attention now. When do we write Taylor forms? When we're writing a tangent line. So this is a form of a line. When we have Taylor form, it's when we write equations of tangent line. And remember, it's y equals y sub 1 plus the slope m times x minus x sub 1. And so that is really just the point slope formula that is solved for y. But Taylor form, equation of a line, this ends up being a degree 1 or a first degree Taylor polynomial. There are Taylor polynomials of higher degree than degree 1. Now, what did we use these equations of tangent lines for? Do you remember? To find an approximation of a point. So like, let's say we have a curve that looks like this, and we're trying to figure out what this value is right here. But we don't really have the equation of the curve, unfortunately. We don't have it. But we do have some information about how fast the curve changes. Namely, we have the derivative equation. So the first method that we did then is we wrote the equation of the tangent line, and we used the equation of the tangent line to approximate the function. So we found this value here as an approximation of that value there. And this would be the error. And we were able to determine if that was too big or too small based on the concavity of the curve. So that would be kind of walking out in one step to the point we're trying to find. So we called this, let's label this right here. I'm going to call that x equals c. It's the point of tangency, but I'm going to let c now stand for the center. It's going to be the center of what we're calling our approximation. The center of the approximation. So c for center. So basically, if I know the function value there and I know the slope there, I can write a tangent line and I can use it to approximate the function value on either side by some amount. I'm going to call it r, plus r minus r, where r is a radius. Does that make sense? And the idea is, if you are within a certain distance of the center of approximation, the tangent line values become decent approximation of the function values. Now, the farther away you get, the worse the approximation in general. And the closer you are to the center of approximation, the better the approximation. But it is only approximation, because the only place where the function f of x you're trying to approximate and the tangent line, which I'll call L of x, they are only the same at c. That's where they're exactly the same. Left and right of that, they're approximations. Now, if we want a better approximation, what did we do in BC here that AB didn't do to give us a better approximation? Euler's method, very good. Euler's method still uses lines, but it chops it up into multiple steps. So you recalculate, and you basically hug the curve in smaller steps, but still with lines, okay, which lines are degree 1 polynomials. So in this section, we're going to learn about Taylor polynomials, which is another way to approximate a function by using maybe not a line in multiple steps, but a polynomial of higher degree, like a quadratic or a cubic. So with that idea, maybe there is a quadratic equation that approximates this function f of x. So maybe there's a, let's say, parabola that looks like that. And if I can find the equation of that parabola, then I can use it to approximate the value on either side of the center with better accuracy than the line. And then maybe if there's a quadratic that fits the curve, maybe there's actually a cubic polynomial that fits the curve even better. In which case, I can use the cubics function to get better and better approximations, and so on and so forth. Maybe there's a fourth degree polynomial or fifth degree polynomial that I can use to essentially wrap around the curve of f of x and use its value to approximate the function value. And that's the idea of what a Taylor polynomial is. We're going to be using polynomials, which are in general easy to work with. They're the easiest functions to work with. They're the easiest functions to evaluate. And we're going to be coming up with polynomial curves that approximate non-polynomial functions like sine of x, e to the x, cosine of x, natural log of x, things that back in the day were hard to work with. So the idea being, if you can approximate it with a polynomial, it's going to be a lot easier to calculate those numbers. All right? So to motivate that, let's look at example 1. It says, find the equation of the tangent line for f of x equals sine of x at 0, and then use it to approximate sine of 0.2. Is it an over or an under approximation? So this is a review. Y'all go ahead and do it. I'll catch up with you. I'm going to go ahead and sketch the graph so I can talk about it graphically while y'all do y'all's computations. Ready, set, go. Bless you. Okay, so while y'all are finishing up the computation, if you want to take a break real quick, I'll let you finish up and I'll catch up with you. What we're doing is we're trying to approximate sine of 0.2. So I drew Sahala, sine, in green. Remember, it starts at the origin, axis high, axis low. And we're trying to approximate sine of 0.2. So what is sine of 0.2 radians? We take it for granted now. We can just type it into the calculator and boom, it spits out something that's accurate to more than 3 decimals. But back in the day, that was an interesting question. I know that sine of 0.2 is a positive number between 0 and 1. But what positive number? If I needed to get more accurate, it was really hard. So using lines would be kind of the most rudimentary way to approximate it. If you can write the equation of the tangent line centered at 0. Now, why would we center it at 0 as opposed to centering it at 0.1? Because at 0, we know what the sine value is, right? What's sine of 0? Sine of 0 is 0. So 0, x equals 0, becomes a good center for our approximation because A, it's close to 0.2, and it's an x value for which we know the sine value. So they had to choose their own center. So if I centered my approximation at 0, sine of 0 is 0, so the point is the origin, and now all I need is the slope. So the derivative of sine with respect to x is cosine. And I also know what cosine of 0 is. Cosine of 0 is 1, so that's my slope. So here would be the equation of the tangent line in Taylor form. It's the y value 0 plus the slope of 1 times x minus 0. That's the standard write-up, but of course, we simplify that to just x. That's your 45-degree line. So now, if I want to approximate the sine function in the neighborhood of 0, the center of my approximation, the line becomes a relatively decent approximation of the function. 0.2 is relatively close. It's only 0.2 away. Now, I drew it further to the right just to kind of show you the difference. But what we're doing then is we really want to know what sine of 0.2 is. I don't know what it is, but I do know what L of 0.2 is. So L of 0.2 becomes an approximation for sine of 0.2. And, of course, that's just 0.2. And then, of course, we know based upon the concavity, the graph of sine is concave down in the neighborhood of 0 to 0.2. So therefore, the tangent line is above the curve. And we know that 0.2 is going to be close, but slightly too big, right? Slightly too big. All right, so let's see what sine of 0.2 is. Let's take it for granted, right? Sine of 0.2. Boom. It's 0.198. Sine of 0.2 is equal to 0.198. Now, if we compare, I mean, we have this luxury now of comparing. We're not going to be talking about an error bound just yet. That's the last thing we talk about. There is a way to determine an error bound, like we did before. Like if we approximate it with the line and get 0.2, we could then figure out eventually how close is that to the actual value. Well, right now we'll just compare. It's 0.98. That's pretty darn close, right? So what is sine of 0.2? Rather than saying, I don't know, it's somewhere between 0 and 1, we could say it's a little bit smaller than 0.2. That's pretty good, okay? Well, let's go ahead and on the calculator now, let's go ahead and graph the following, adding one term at a time. So I'm going to walk you through this, okay? We just have right now y equals x graphed in our calculator. Let's go ahead and add this next term. Let's go ahead and add minus x cubed over 3 factorial. And set your window. This is a nice viewing window. -9 to 9 and -4 to 4. Okay? So I'll go ahead and set my window first. -9 to 9. And I'll count by ones and then -4 to 4. All right, so now I need to go to y equals. I'm going to go ahead and sketch sine of x in y1 because I want to kind of do some comparison here. And in y2, let's graph x. Okay, so while y'all are doing that, there's what we just graphed by hand. Okay, so again, notice they have the exact same value at the center. The line's value at 0 is 0 and the sine value at 0 is 0. But after that, they deviate. Now you can actually see on the calculator kind of where the radius is, where you can get decent approximations because the curves overlap. You wouldn't use this line, though, to approximate sine of 2 pi, would you? Because 2 pi is way over here, and that's a horrible approximation. So there is this window in which you get a decent calculation. Now, let's come down here, and let's add that next term. Minus alpha y equals x cubed. You don't have to know where these terms are coming from just yet. Just know that they're there. So 3 factorial, remember, you can hit math probability 4 or hit alpha window. Thanks to Skylar, I didn't even realize this. Alpha window number 9. So what we have now in y2 is not a linear function, but rather a what? Polynomial. That's a cubic polynomial, right? The coefficient would be -1, 6. 3 factorial is 6. So that's a cubic polynomial with a negative coefficient. Let's see what it looks like. Hit graph. There's sine of x. Oh, what do you notice about the red graph now compared to the blue graph? They're pretty close to each other in the neighborhood of 0, aren't they? And then they deviate. Well, they have the exact same value at 0. If you want to verify that, if you plug a 0 into the polynomial, you get 0 minus 0. So they still have the exact same value at the center. But what's happening now is this cubic function is wrapping itself around, kind of like a boa constrictor would, if you were giving it a hug on pet day. It's wrapping itself around the sine curve. Not completely. They are not the same, but they are so close that my calculator can't even show the difference between the red and the blue. But they are different everywhere except 0. So the idea now is if I wanted a better approximation of sine of 0.2, I can plug it into x minus x cubed over 3 factorial. And it's a little bit more work, but I can still handle 0.2 cubed without a calculator. A little bit more work, but it gives me a better approximation. Well, what if I wanted a better approximation? Is there a polynomial of higher degree that would give me a better approximation? Well, yeah, there is. Let's go ahead now to y2 and add the next term in that sequence or series, which is plus. And now it's x to the 5th over 5 factorial. And you might see a pattern emerging right away. Okay, so now this is a 5th degree polynomial with a positive leading coefficient. Now, this is going to look even better. Notice they have the exact same value at the center, 0, but now this fifth degree polynomial appears to be wrapping itself around the graph of sine on a larger interval. They're only the same at the center, but they are really, really close to each other left and right. So if you wanted to know what sine of point 2 is, let's go ahead and try it out here. If you hit the trace button, hit sine of point 2, there it is. We know it's 0.198. Click up to the red curve and type in 0.2 again. Notice it's also 0.198. So doing these calculations by hand for a fifth degree polynomial, it would take a little bit longer, but because it's a polynomial, it's still preferred. You can actually get a really good approximation. Okay, let's keep going then. If you wanted a better approximation and you were okay with doing just a teensy-weensy, that's a small amount, teensy-weensy. You got teensy, and then you got teensy-weensy. Add one more term. The next term would be x to the 7th, all over 7 factorial. Now this is going to be a 7th degree, what we call Taylor polynomial, with a negative leading coefficient. Hit graph, and you'll see now that it's wrapping itself around the graph of sine of x a little farther out. So if you wanted to hit trace, type in 0.2 again. Oop, not 0.22. 0.2. You get 198.6693. 198.6693. Click up. 0.2. 198.6693. Holy moly. With a 7th degree polynomial, they're not really supposed to be the same, but our calculator is not storing or showing enough digits. These are already the exact same to 1, 2, 3, 4, 7 decimal places, just by going out to a 7th degree polynomial. So if you wanted that level of accuracy, you could go out a little bit further. Why are we using polynomials instead of just calculating sine of 0.2? What's easier to calculate, sine of 0.2 or plugging and chugging a 0.2 into this equation? Plugging and chugging is a lot easier, yeah. In fact, have you ever wondered how your calculator comes up with sine of 0.2? Is your calculator, is it pre-programmed with sine tables? Guess how your calculator computes sine of 0.2? Your calculator actually computes sine of 0.2 by using this method right here. It is programmed to do this. Now, I don't know the level of accuracy that it goes out to. Maybe it only goes out to a 7th degree polynomial. But this is how your calculator is programmed to compute sine of a number, cosine of a number, tangent of a number, e to a number, all those crazy transcendental functions, we call them, that aren't polynomials. It uses polynomials in its program to evaluate it. That's pretty awesome. So it's still relevant today for programming purposes. All right. Now, that's all I have listed, but I'm pretty sure you savvy BC kids can come up with the next term if we needed to add another one. What would it be? Plus, very good, x to the 9th, all over 9 factorial, alpha window 9. Let's go ahead and add another term. What would the next one be? Minus. Good. So you're seeing the pattern. Notice that sine of x was what? Even, odd, or neither. What type of symmetry, bless you, did it have? It was an odd function. It had an origin symmetry. What do you notice about all these polynomials that we're using to approximate it? All the powers are odd, which means the functions themselves are also odd functions. Yeah. So we're taking an odd function of sine and we're approximating it with an odd polynomial, which is why there's no even degree terms there. What else do you notice about the signs? They're alternating. So there is an alternating series that we're going to memorize for sine, and it's an alternating, as you can clearly tell, and it starts with x to the 1st. So what would the next one be? Let's go out one more here. X to the 13. We'll stop at lucky number 13. Wait. Code 2. Hang on. I messed myself up trying to talk at the same time. X as calculating. Okay, I'm doing it again. 13 alpha window 9. Okay, so this is many, many terms. So as you might expect, this wraps itself around the graph of sine, starting way out there. All right, so now we're basically extending our radius. Our center of approximation is 0. But as we get a higher and higher order polynomial, we're giving ourselves the freedom to approximate sine of 2 pi if we wanted to, right? Notice 2 pi is over here. All of a sudden, sine of 2 pi and the polynomial of 2 pi are pretty darn close. Now, that wouldn't be good practice. If you wanted to approximate 2 pi, you could change your center of approximation to something that's closer to 2 pi. Well, we already know what 2 pi is. 2 pi actually would make a good center because we know what the sine value is, right? So guess what happens if you were to continue this forever and ever and ever using the same pattern with infinitely many terms? Guess what would happen? They would be the same. Exactly. So if you added infinitely many terms, which is physically impossible, it would actually become the graph of sine, not just an approximation for it. So that's called the Taylor series. What we're doing when we have a finite number of terms, we're coming up with Taylor polynomials of a finite degree, and they then just become approximations. They look like they're exactly the same. And if you trace with your calculator, you're not going to see the difference in the decimals because they're so close to each other near 0. But keep in mind that they are only truly the same at the center 0. Left and right of that, they just become approximations, okay? So that's the idea of a Taylor polynomial. So all this time when we were writing Taylor form, we were just doing first degree approximations, okay? But there are higher orders out there. All right, so now you know what a Taylor polynomial is. Let's see if we can figure out where these terms come from. Like, who came up with those terms? How did someone figure that out? Good question. Enter this guy. We're going to do him first. Aren't you envious of his hair? That might be a wig, but I hope it's not. I hope he sported that every day. Okay? This guy's name was Mac Daddy Maclaurin. Okay? Colin Maclaurin, right, Colin? Yeah, there you go. Scottish mathematician Colin Maclaurin. He's the guy that came up with the original form for something that's centered at the 0. He came up with a polynomial equation for something that is centered at 0. So here was his formula. He called the polynomial p, and then the subscript n is the degree of the polynomial. He said if you want to write a polynomial for any function f of x, it's going to be the y value plus the slope times the x value, which is x minus 0. So this right here is what we've been doing all year long, right? This is y sub 1 plus m times x minus 0. X sub 1. It's the exact same thing. But now we can add more terms. Plus the second derivative at the center over 2 factorial times x squared. Plus, guess what the next one would be? The third derivative at the center over 3 factorial times x cubed. Plus the next one would be the fourth derivative. And remember, we go to kind of parentheses there. The fourth derivative at the center over 4 factorial times x to the 4th. Let's go one more term. Plus the fifth derivative at 0 over 5 factorial times x to the 5th plus yada, yada, yada. Do you see the pattern? So here's the nth term. This is how he's generating it. In general, and this is the powerful part, to generate any term that you want, so to be as accurate as you want, the terms are just going to be of this form, which is going to be the nth derivative at 0 over n factorial. This right here is going to give you, oops, I circled too big. This right here gives you the coefficients, and then times x to the n, this is your variable. Can y'all memorize that pattern? The nth derivative at 0 over n factorial times x. Now this is centered at 0, so that's called a Maclaurin series, or a Maclaurin polynomial if it has a finite number of terms. That's really the only difference. I kind of use them interchangeably, but what's important to realize is that a series has infinitely many terms. A polynomial just stops at a degree n, which is a finite number of terms. So we called that a Maclaurin series, an nth degree Maclaurin polynomial, all right? So then someone else came behind him and said, great hair, no thanks though, and said, you know, I want to center my approximation at not 0. What to do then? Well, enter Brooke Taylor. who said, I don't have any hair, so I wear a dishcloth on my head. Okay? Just whatever was laying around. Okay? You talking to me? This kind of looks like Zuckerberg yesterday in front of Congress, doesn't it? Or today. Yeah, today. He's back today. So here's what he said. Let's say that you want to center it in general, not at 0, but at C, where C is any number in the whole wide world. Then a polynomial of degree n, centered at C, is going to be very similar to MacDaddy's. It's the y value at the center plus the slope, f prime at the center, times x minus the center. And this is what's known as the Taylor form of the first degree polynomial. Notice we list it in increasing form. We start with the constant, and then we go to the first degree. Now, if you want to add more terms, the pattern really picks up when you get to the second derivative. It's the second derivative at the center over 2 factorial times x minus the center squared, plus what would the next one be? The third derivative at the center over 3 factorial times x minus the center cubed. Let's go a couple more just to reinforce it. The next term would be the fourth derivative at the center over 4 factorial times the x minus the center to the fourth. And one more. Let's move it around here. The fifth derivative at the center over 5 factorial times x minus the center to the fifth. And now plus dot, dot, dot. This is like, if you're going to memorize one more thing the rest of this year, and then you're going to check out whatever, check this out before you check out, okay? That's what you want to memorize. That's like golden. That's the distilled product of Maclaurin's pioneering work, and then later extended by Raghead, okay? The nth derivative at the center over n factorial times x minus the center to the nth power. That's how you could generate any term of any function that's differentiable, because you need the derivatives at C, to the nth power. So that pattern actually holds up with the first one. This would be the 0th derivative at the center over 0 factorial. Plus, this would be the first derivative at the center over 1 factorial times x minus c to the first. But why do you not see the pattern there? Because what do we call the 0th derivative? It's just a function value, actually. The 0th derivative is also known as the function value. It's like, don't take the derivative. Okay. And then divided by 0 factorial, what's 0 factorial? 1. Okay. So we don't really pick up on the pattern in full force until the second derivative. And then, of course, the next term would keep the same pattern. F prime of c we know, but what's 1 factorial? 1. So then x minus c to the first, we don't show it. So really, when we start generating these things, the pattern holds for all terms. But the way I teach it to you is, if you ever needed to go past a linear, you're going to go ahead and write the equation like we know, the y value plus the slope times x minus the c value, and then we're going to pick up with this pattern, which is going to then maintain itself. The second derivative over 2 factorial, x minus c squared. Third derivative over x minus, or 3 factorial times x minus 3 cubed, so on and so forth. Just to distinguish between the two parts, like we did for MacDaddy, these are the coefficients. These are the coefficients. And these are your variables. Okay? And so because Brooke came first, Maclaurin came first, Colin did, and then Brooke came second and extended it. That's why we typically call these Taylor polynomials. But sometimes it might just say, write a Maclaurin polynomial or write a Maclaurin series. So if you ever hear Maclaurin, they're not going to tell you what the center is. So whenever you hear the word Maclaurin, you think the center is at what? 0, always, okay? So a Maclaurin series, a Maclaurin polynomial, centered at 0 all the time. It's not going to be stated. That's one of the things you have to know. Now, they could say write a Taylor polynomial centered at 0, and you'd be like, Maclaurin, right? Okay? Just like when they say Newton invented calculus, you go, Leibniz. Same thing. Yeah, now it would be kind of silly. Imagine if this was discovered in the reverse. If Taylor came along first and said, at any value of C, you can use this, and Maclaurin's like, I'm going to use a special case and call it C equals 0 and name it after myself. That would be kind of silly. That would be kind of like, I don't know, L'Hopital learning a rule from Johann and then publishing it and calling it his own, which actually happened. Okay, so if you're into reading and you want the history behind it, there you go. I included some historical vignettes for your reading pleasure. Should I choose one of y'all to stand up and read aloud like we did back in the old days and get through this? I think we should start with Colin in honor of Colin Maclaurin. They kind of look the same, don't they? If you just kind of give some speckled beard. Yeah, okay. Here's what we know about both of them. Eye, heart, calculus. Right? Yeah. Okay, sweet. Let's try it out. Let's see, we have time. Let's see where these terms come from, shall we? Where do these terms come from? Not from France, but from Britain. They come from Taylor. They come from, bless you, Brooke Taylor or Colin Maclaurin, either one, because we centered ours at 0. So let's go ahead and generate those terms. Here's what you're going to do. It says to find the Maclaurin polynomial of degree 5 for sine of x. Now, it didn't say the center, so we know we're centering at where? 0. So here's what I want you to do every time. Let's get our machinery in order before we use it. Machinery in order. Identify the center. It's probably the most important piece. The center is 0. Okay? We're going to make some columns here. So f of 0 is sine of 0, which is what? 0. Okay? Now, next door to that, take, underneath that, actually. Let's go underneath that. F prime of x, let's do that first, is what? Cosine of x. So now next door to that, what's f prime of 0? What's cosine of 0? 1. Yeah. I'm going to scoot this over because we don't need to. There we go. So here you could actually say f of x equals cosine of x. What's another name for f of x? The zeroth derivative of x. Okay? Same thing. Oh, yeah, sine of x. Thank you. So really two columns, the variable part and then next door to it, evaluating it at the center. All right, so then the second derivative is what? Negative sine. And now next door, the second derivative at 0 is negative 0, which is 0. The third derivative, the derivative of negative sine is negative cosine. The third derivative, evaluated at the center then, is negative cosine of 0, which is negative 1. Now, how far out do we need to go? It said we need a fifth degree polynomial, so we need to get out at least to the fifth derivative. So let's keep going. Now we switch to Arabic with parentheses. The fourth derivative of x is back to positive sign. So then the fourth derivative at 0 is sine of 0. Sine of 0 is 0. And then the last one, the fifth derivative of x, is the derivative of sine, which is cosine. And then the fifth derivative evaluated at 0 is cosine of 0, which is back to 1. So what we're doing here, we're not generating our coefficients of the polynomials. We're generating the whats. These are the whats of the coefficients. Numerators, yeah. This is generating the numerators. That's very important. Let's write that out there. These are the best numbers. No, these are the numerators. I get distracted easily. These are the numerators of the coefficients. We don't really need to generate the denominator separately because it's just n factorial as we go. All right, so now I think we're ready to use those dudes. So here we go. Sine of x can be approximated by. Now that's the important thing. Whenever you're using a Taylor polynomial, you are always on squiggle alert because polynomials only approximate. Later on with the series, we're going to be able to put equal signs there. But right now, sine of x is approximated by. Let's give it a name. Let's call it m sub 5 of x. M for Maclaurin. Oh, did it already give us? Oh, it said to call it p sub 5. Okay. Sorry, Maclaurin. I was trying to give you a tribute. But yeah, if they give you a name, use it. If not, name it. Now, P is for polynomial. That's generic. So typically you can call the Maclaurin polynomial M, just to remind yourself, and a Taylor polynomial you can call T of X for Texas, or for Taylor of X. But P is generic for polynomial. The subscript gives you the degree, all right? So here we go. We're going to start by writing the equation of the tangent line, which is the y value of 0 plus the slope. What's the slope? 1 times x minus 0. I'm going to go ahead and write it out like that, to the first power. All right, so there would be the equation of the tangent line. We've already written that, haven't we? But now we're picking up with 2. So what is the numerator of the degree 2 term? It's 0. So plus 0 over 2 factorial times x minus 0 squared. What is the numerator of the next term? The cubic term. Negative 1. So now we get, I'm just going to say minus 1 over 3 factorial times x minus 0 cubed. And then what's the coefficient of the fourth degree? 0. So plus 0 over 4 factorial times x minus 0 to the fourth. And then finally, what's the numerator of the fifth term? 1. Okay, so plus 1 over 5 factorial times x minus 0 to the fifth. And we stop. We don't put plus dot, 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 because we have a squiggle over here. It's an approximation. Now, that is a pattern that maybe when you simplifies down to something that you can extend without having to go back and generate more terms. But the beauty of Maclaurin and Taylor's work is that for any differentiable function, you can continue this process and generate a polynomial for it. Okay? So notice that pattern is captured right here. But once you simplify, as I already alluded to, every polynomial generates its own inherent pattern. Okay? So this one, the 0 goes away, so we're left with 1 times x is x. When the numerator, the coefficient of 0, what does that do to that whole term? It wipes it out. So notice that happens with every even term. And so what's left is, let's see, we're left with this term here. So that's going to be minus 1 over 3 factorial. Or let's just call it, how do we do it up here? You can write it as a third. Yeah, we put the x on the top just so there wasn't a 1 there. Yeah, x minus 0. So we wrote that as x cubed over 3 factorial. And then plus the next term's gone. So the last one will be plus x to the fifth over 5 factorial. Bless you. Okay, so that is the fifth degree polynomial for sine of x. So sine of x is approximated by that. And now, if you needed to write a seventh degree polynomial, you probably wouldn't need to come back over here and extend it to the sixth and seventh derivatives, would you? Because as we did when we were typing it into the calculator, you now pick up on the inherent pattern for each polynomial that's created per function. So it's kind of cool. Everyone has two patterns. The Taylor pattern, which is what we use to generate it. And then once we simplify, it gets its own, what I've been calling the inherent pattern. It's genetic DNA, essentially. And so you can extend terms without having to show all the machinery being generated. But we generate the machinery off to the side to get the numerators for our coefficients. Very, very important. All right? So there you go. Pretty cool, huh? We've already done the comparisons on the calculator, so I'm not going to actually show it. But you could say then that sine, let's go ahead and just write it out. Sine of 0.2 then is approximated by p sub 5 of 0.2, which would equal, and now it's just a little bit of writing, 0.2 minus 0.2 cubed over 3 factorial plus 0.2 to the fifth over 5 factorial. And back in the day without a calculator, they would enjoy the opportunity to then sit down and compute that and add it all together and come up with a number. Okay? We've already seen that on the calculator. So I'm not going to actually type that in. But you could. You could type that in and compare it to the actual value sine of 2. All right? Now, pretty cool, huh? I think this is amazing. This is one of the most exciting things that I think we do all year. I just think it's remarkable that someone can come up with a clever workaround. What's sine of 0.2? I don't know, but here you go. Here's a fifth degree polynomial that'll give you pretty much the same thing. How'd you know that? I don't know. I was bored, right? I was bored. It was weekend Twitter. I wasn't really on Twitter that weekend, so I did this, right? Comments or questions on this? What? Okay, sweet. Yeah, I'm taking bold liberties here. I wrote the question, and then I'm defiantly not even reading the question. Yeah, we did point 2 up here. This one asked you for point 1. So you will lose points if you do not actually follow directions. Thank you, Lucy. Wait, what does that be? No. You would lose points for your final answer, for sure. You would get points for generating it, get points for writing it out, but then you would lose points for evaluating it on the follow-through, right? Which I'm really bad. I run the first 26 miles of the marathon, and then I'm tempted by the free T-shirt finishing signs at the end. I almost said free beer signs. But, yeah. Right. Okay. Now pretty cool, huh? Thanks, Lucy. Pretty cool, huh? Pretty cool. Okay, so does such a polynomial exist for any differentiable function? The answer is yes. And you're going to have to memorize a few of them. Sine of x is one of the ones you have to memorize. So without looking, sine of x is approximately x, positive x, and then minus x cubed over 3 factorial, plus x to the 5th over 5 factorial, minus x to the 7 over 7 factorial, et cetera, et cetera. So hopefully you memorize that pattern. Now it says find the Taylor polynomial for degree 6 for natural log at 1, and then use it to approximate the natural log of 1.1. Let me stop there before we get going, because maybe we don't have time for this. We're in here for 5 more minutes. I'll show you one more thing. Yes, Colin, Maclaurin. We should just start calling him Maclaurin or Mac Daddy the rest of the year. What's up, Mac Daddy? Yes. I personally, me? Yes. Or if one was to. Okay. Yes. And do this, would you get the same polynomial? Oh, yeah. If you take a polynomial and generate a Taylor polynomial to approximate the Taylor polynomial, would you get the exact same polynomial? What would you think? I would hope so. I've never had anyone ask such an inane question, and now I think about it, it's actually not inane. It's actually a pretty legitimate question. I've never done that. Do we have time for that? All right, so we may not get to it, but let's say, Colin, pick your polynomial. Okay, hold off right there. Yeah, we don't have that much time. How about this guy? All right, where do you want to center it? Let's center it at 0, shall we? Now, how do we know that we should center it at 0? This is kind of a good giveaway, because these are x cubes and x squareds. If you had said x minus 1 cubed plus 2 times x minus 1 squared, I would say the center is at 1. So one of the things, too, and I'm glad you brought it up, you are going to be expected to spot the center in reverse. So you can always look at the x's. So let's see if we center this at 0, if we get it. So this is a second-degree polynomial. So f of 0 is 0. F prime is equal to 3x squared plus 2x. So f prime of 0, 4x. Is 0. F double prime is 6x plus 4. Is that right? Help me out. Yeah, so that would be 4. And then the third derivative is 6. So F 6. So now if I generate it.
Pardon the interruption. We have an announcement for testing tomorrow. Students, at this time we have room assignments posted in the cafeteria, near the cafeteria lines over where the glass walls are with the horses on or uniforms on it. If you want to check to see where you'll be testing tomorrow, please check that wall. Teachers, we just want a reminder, we need to prep our room, make sure that the desks are facing forward and all things are covered. Students, want to remind you to bring some snacks, sweaters, number 2 pencils, and be ready for that test. Get a good night's sleep, and wish you well on your testing tomorrow. Have a good day, uniforms.
It did come out to be the same. Yeah, it comes out to be the same. The first term goes away, so it's the y value 0 plus the slope, which we said was 0, times x minus 0, or x to the first. And those two go away, and then we're left with 4 over 2 factorial, which is 2, x squared. 3 factorial 6, so 6 sixths is 1, we get x cubed. So yeah. So it's kind of silly, but it actually is kind of cool. I've never done that. 20 years of teaching this, no one's asked that. So there you go. He does have a little stroke of Maclaurin in him, I guess. Yeah. So we would call this the basis if we were trying to prove this by induction. It works for itself, all right? And it also works for other things. So fascinating idea. Go ahead and turn your calculator in, and we'll pick up there tomorrow.